Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today we're going to take a quick look at a hydraulic system making use of a proportional valve to control the acceleration and deceleration of a hydraulic double-acting cylinder. This lecture operates under the assumption you've watched the Introduction to Proportional Valves lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet, only dimly recall its contents, please take the time to do so now. As you're no doubt aware, proportional valves are electrically actuated infinitely variable valves that simultaneously influence flow rate and direction. By progressively ramping up and down applied voltage to the proportional valve, the acceleration and deceleration properties of actuators can be controlled. Consider a three-position proportional valve making use of a spool positioning device known as a linear force motor and intended to operate inside a continuous range of positive to negative 10 volts. The polarity of the applied voltage determines the direction of spool movement, and magnitude of the applied voltage determines the distance. Let's assume the application of positive voltage moves the spool into the straight-through P to A position, and the application of negative voltage moves the spool into the cross-connect P to B position. A 0-volt differential perfectly spring centers the spool in the closed center position. Intermediate values between full positive 10 volts and full negative 10 volts produce proportional, hence the name, intermediate flow rates. A graph of flow rate as a function of applied voltage includes several noticeable characteristics, principally deadband, hysteresis, and some minor nonlinearities. Deadband is a region of zero flow despite increasing magnitudes of applied voltage. Deadband is a byproduct of several non-negotiable realities like spool overlap and friction. The flat zone characterizing the deadband means a certain minimum amount of voltage must be applied to the proportional valve for it to open at all. Hysteresis, in contrast, is a spool's tendency to displace differing amounts when applied voltage is increasing in magnitude than when applied voltage is decreasing in magnitude. The use of internally generated feedback from a spool position transducer, like a linear variable differential transformer, LVDT, minimizes observed hysteresis. The LVDT, an internal closed-loop control of spool position, may or may not be explicitly illustrated in the schematic diagram. Finally, because the proportional valve is inducing a restriction, quite like a regular flow control valve, we can expect a double-acting cylinder to actually extend faster than it would retract given equal applied loads. The cap end, having larger functional area, necessitates less pressure to move a given load. This means the proportional valve will experience more of a pressure differential during extension at a given applied voltage and more flow as a result. The observant among you will notice that the straight-through P to A position curve is slightly steeper than the cross-connect P to B position curve. This is assuming that actuator port A is attached to the cap end of the cylinder and actuator port B is attached to the rod end. For our purposes, though, let's consider this pretty negligible. Note there additionally exist pressure-compensated proportional valves that keep flow rate constant regardless of changes in pressure above stream and load-induced downstream variations inside a given range. As mentioned in the above referenced lecture, the pressure shock associated with traditional fully closed or fully open directional control valves can be mitigated by smoothly ramping applied voltage up or down over time delivered to a proportional valve, thereby slowly opening or closing the valve and suppressing the pressure shock. This progressive increase or decrease in flow rate also directly lends itself to the controlled acceleration and deceleration of the applied load. When applied voltage is plotted with respect to time, note this actuator would be performing two separate actions, an extension phase followed by a retraction phase. Note the extension phase is divided into three separate subphases: acceleration, constant speed, and then a deceleration. And the same can be said for retraction. Ramping up or down applied voltage to a proportional valve over time, rather than simply slamming it on or off at full flow, results in controlled acceleration and deceleration of the applied load. This could be used to smoothly and precisely position a critical actuator without risking mechanical stress or damage. Ramp generators are part of the proportional valve controller that influence the acceleration and deceleration characteristics of an actuator. A ramp generator is quite simply a steadily increasing or decreasing applied voltage over a specific length of time. The shorter the length of time to or from full voltage, the more sudden and abrupt the acceleration or deceleration event. The longer, the more gradual and smooth. If the acceleration and deceleration rate can be properly adjusted for a given travel length and flow rate, theoretically the actuator will fully extend and retract smoothly and exhibit no pressure shock. Allow me to demonstrate using hydraulic circuit making use of a proportional valve. Let's first perform a brief walkthrough of the system. Keep in mind, I have purposely simplified this system into functional blocks, specifically elements within the proportional valve controller. This level of compartmentalization will keep this discussion on track within a realistic amount of time. We could go into exhausting detail about any one of these components. However, let's just treat them as ideal entities right now that just accept inputs and deliver outputs. Later lectures in power electronics and industrial controls will discuss these entities in greater detail. First, note the primary hydraulic circuit incorporates two limit switches, LS1 and LS2. These are sensory devices with the intention of initiating the transition from full speed to deceleration mode during extension and retraction. Just so we've got some numbers to deal with, let's say the travel length of the cylinder is 8 inches. Note LS1 is, let's say, 2 inches from full extension. And let's say LS2 is 2 inches from full retraction. LS1 initiates the extension deceleration period, and LS2 initiates the retraction deceleration period. Let's assume this system makes use of 24-volt DC pilot ladder logic to govern its operation. Rungs 1, 2, and 5 control the extension of the cylinder. Rungs 3, 4, and 6 serves to initiate and control the retraction of the cylinder. The normally closed stop button in rung 1 would serve to deselect a given mode on the off chance you want to stop the cylinder mid-travel, or happen to accidentally select extend at full extension, or retract at full retraction, or tried to simultaneously extend and retract the cylinder. All scenarios that don't make much sense. Again, this circuit is for illustration purposes only. This is not meant to be an industrially proven circuit by any means. A truly robust and functional circuit would necessitate some level of interlocks to prevent these scenarios from happening. Note, both the controller and proportional valve would ordinarily necessitate continuous connection to external power for their internal components. These power connections are not shown on this diagram for the sake of simplicity. Before examining the system's operation, let's zoom in on the proportional valve controller for a moment. Internal to the proportional valve controller, the block diagram for the positive and negative ramp generators each include an enable input as well as an output. The outputs of both ramp generators are tied to the linear force motor on the proportional valve. Note, we are assuming the proportional valve controller has an interlock between the positive and negative ramp generator, in that if one ramp generator is currently enabled, the other will be disabled. This is where serious simplification comes into play. Note, the proportional valve controller necessitates internally generated or externally supplied positive 10 and negative 10 volt set points, respectively employed by the positive and negative ramp generators. Theoretically, one could include portions of the proportional valve controller in the ladder logic diagram, but I find it messy and confusing since you're using a mix of digital 24 volt DC and continuously variant positive to negative 10 volt DC. It's best to keep separate worlds separate. Note, however, quite like the interaction between the primary hydraulic circuit and the pilot ladder logic, the limit switches being the principal examples, there exist interaction points between the pilot level ladder logic and this proportional valve controller. Notably, normally open contacts CR1B and CR2B. Let's assume the positive ramp generator, on being enabled by a 24 volt DC input with a closure of contact CR1B, immediately begins the desired ramp up sequence from 0 to positive 10 volts over the desired period. And when this enable input is de-energized, immediately begins the desired ramp down sequence from positive 10 volts back down to 0 volts over the desired period. Again, the closure of contact CR1B serves to enable the positive ramp generator. Similarly, let's assume the negative ramp generator, on being enabled by a 24 volt DC input via the closure of contact CR2B, immediately begins the desired ramp up sequence from 0 to negative 10 volts over the desired period, and when this input is disabled, begins the desired ramp down sequence from negative 10 volts back down to 0 volts over the desired period. The closure of contact CR2B serves to enable the negative ramp generator. Just so you know, I'm not an idiot. I'm just being super flexible with the terms up and down. By ramp up, I mean going from 0 to a respective maximum. Similarly, ramp down is meant to imply going from maximum back to 0. This way I can use the same terms for both extension and retraction actions. You'll note the timing diagrams for both ramp generator outputs are essentially executing a modified off-delay timer in that it delivers an immediate output upon being energized. However, upon being de-energized, continues to deliver output for a measurable delay period. For those not seeing this connection, here's the timing diagram of an off-delay timer. The similarities with a normally open, time-open contact are readily apparent. For those wishing to review off-delay timers are encouraged to check out the Timers Off-Delay lecture available at the Big Bad Tech channel at their earliest convenience. The only real difference about the output of the off-delay timer in a ramp generator is that the ramp generator is producing a ramp transition from 0 to the respective positive or negative maximum and back again over a specific time period rather than an immediate off to on and on to off. Let's assume that the ramp up and ramp down period are symmetrical and that there is one adjustment point and the ramp up time equals the ramp down time. Additionally, let's assume the single adjustment point allows for values from 0 to 10 seconds. I should note that not all block diagrams of elements within a proportional valve controller are drawn using the same approach. For example, a ramp generator inside a proportional valve controller can also be depicted as a single ramp generator which executes a timed ramp to or from whatever value is applied to its input. For example, if this single ramp generator has positive 10 volts applied to its input and is set to 5 seconds, its output goes to positive 10 volts over the course of 5 seconds. When the input is disconnected, the output drops from positive 10 volts to 0 volts over the course of 5 seconds. Similarly, if this single ramp generator has negative 10 volts applied to its input and is set to 5 seconds, its output goes to negative 10 volts over the course of 5 seconds. When this input is disconnected, the output goes from negative 10 volts to 0 volts over the course of 5 seconds. This block diagram using a single ramp generator is basically tying together the enable and source for what would ordinarily be split into two separate ramp generators. Long story short, they do the same thing, however they use different means of depicting this function. I'm going to stick with two separate ramp generators for the purpose of this analysis since I find it easier and it doesn't necessitate any changes to our existing ladder logic diagram. Again, our goal is threefold. 1. To smoothly accelerate and decelerate the applied load. 2nd, to fully extend and retract the cylinder. And finally, minimize pressure shock. We'll do this in 4 different iterations of ramp generator transition times. Way too short, way too long, just a little too short, and just right. This multi-step analysis might seem time-consuming, but each progressive step yields important intermediary results that might not be as obvious if we jump right to the conclusion. Anticipation, as they say, is part of showmanship. Let's start out with an obviously poor attempt at reaching these goals. Let's set the ramp generator to 0 seconds, meaning when either ramp generator is enabled, its output instantaneously goes from 0 to its respective maximum, and when de-energized, its output instantaneously goes from its respective maximum back to 0. Those of you with even the slightest understanding of proportional valves will recognize this situation as lost to cause as your lab partner being asked to use an ammeter during a lab practical. Note when the proportional valve is in the closed center position, pressure upstream is that of the main pressure relief valve, and the double-acting cylinder is locked in the fully retracted position. Let's say the main pressure relief valve is set to 250 psi. Additionally, remember we're assuming that the travel length of this cylinder is 8 inches. Realize these are just arbitrarily generated values, and the behavior of this system is for illustration purposes only. You'll be pleased to know I am trying to avoid heavy calculations in the interest of expediency. When an operator presses extend, the coil of control relay CR1 is energized. Its associated contacts immediately change states. Contact CR1A closes and establishes a holding circuit, which allows an operator to release the extend button. Simultaneously, contact CR1B closes and enables the positive ramp generator set to execute a 0-second ramp. Applied voltage to the linear force motor on the proportional valve immediately goes from 0 to positive 10 volts, and the spool is fully shifted to the straight-through position. Flow rate goes from 0 to maximum, and the cylinder applied load suddenly jackrabbit to a start. Pressure immediately drops to that necessary to extend the applied load. Let's say 100 psi is sufficient. The cylinder extends. 2 inches into the 8-inch stroke, the applied load strikes LS2, but no output is observed since normally open contact CR2A is still in the deactivated open state. Leaving the reset region of LS2, LS2 recloses. 6 inches into the extension stroke, the applied load strikes LS1. LS1 opens, and the coil of control relay CR1 is de-energized. The contacts associated with control relay CR1 immediately return to their deactivated states. Contact CR1A opens and removes the holding circuit. Simultaneously, contact CR1B opens and signals the positive ramp generator to execute a 0-second ramp down. Applied voltage to the linear force motor in the proportional valve immediately drops from positive 10 volts to 0 volts, and the spool is fully shifted to the closed center position. Flow slams to a halt, as does the applied load. Pressure upstream of the proportional valve spikes to that of the main pressure relief valve. Quite obviously, we failed to meet every qualification during the extension phase. 1. The applied load didn't accelerate smoothly, but rather jerked to a start and slammed to a stop. 2. The pressure dropped, then spiked. Finally, 3. The rod failed to fully extend. All in all, an unqualified failure, and we're only halfway through. The retraction phase is the same song, only played in reverse. When an operator presses a retract, the coil of control relay CR2 is energized. The contacts associated with control relay CR2 immediately change states. Contact CR2A closes and establishes a holding circuit via the normally closed LS2 contact. This holding circuit allows an operator to release the retract push button. Simultaneously, contact CR2B closes and enables the negative ramp generator set to execute a 0-second ramp. Applied voltage to the linear force motor in the proportional valve immediately goes from 0 to negative 10 volts, and the spool is fully shifted into the cross-connect position. Flow rate goes from 0 to maximum, and the cylinder applied load suddenly jackrabbit to a start. Pressure immediately drops to that necessary to retract the applied load. The cylinder retracts. Leaving the reset region of LS1, LS1 recloses. No change in state is observed, since contact CR1A is still in its deactivated open state. 2 inches away from full retraction, the applied load strikes LS2. LS2 opens and the coil of control relay CR2 is de-energized. The contacts associated with control relay CR2 immediately return to their deactivated states. Contact CR2A opens and removes the holding circuit. Simultaneously, contact CR2B opens and signals the negative ramp generator to execute a 0-second ramp down. Applied voltage to the linear force motor in the proportional valve immediately goes from negative 10 volts to 0 volts, and the spool is fully shifted into the closed center position. Flow slams to a halt, as does the applied load. Pressure upstream of the proportional valve spikes to that of the main pressure relief valve. The rod stops 2 inches from full retraction. Again, quite obviously, we failed to meet every qualification during the retraction phase. 1. The applied load didn't accelerate or decelerate smoothly, but rather jerked to a start and slammed to a stop. 2. The pressure dropped, then spiked. Finally, 3. The rod failed to fully retract. Again, an unqualified failure. For data-driven individuals, here's what a graph of velocity and rod displacement would look like during these periods of extension and retraction. Note velocity starts from 0 and immediately goes to a respective maximum. Given these periods of constant velocity, rod displacement steadily increases to the final travel length. Note it stops just short at 6 inches, and in retraction it stops just short at 2 inches. At these points of partial extension and partial retraction, velocity immediately crashes back to 0. These are obvious simplifications, but you should get the picture. The larger point being that the sudden transition from 0 to maximum speed is meant to imply that acceleration is astoundingly abrupt, as is deceleration. The clear problem in our previous implementation is that the ramp generator is producing way too quick of a transition. Let's see if we could have another go. As they say, for every action, there is an equal and opposite overreaction. Let's therefore swing wildly in the opposite direction and set the ramp generator to a transition time as high as we can. Let's say the ramp generator is now set to execute a 10-second ramp up or down. Starting from a fully retracted condition, when an operator presses extend, the coil control relay CR1 is energized. The contacts associated with CR1 immediately change states. Contact CR1A closes and establishes a holding circuit via the normally closed LS1 contact. This holding circuit allows an operator to release extend. Simultaneously, contact CR1B closes and enables the positive ramp generator set to execute a slow 10-second ramp up. Applied voltage to the linear force motor does this super slow crawl from 0 to positive 10 volts over an agonizing 10 seconds. Slowly, 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 the spool is shifted into the straight-through position. At a certain minimum voltage, the dead band is passed and the proportional valve cracks slightly open, allowing a minimum amount of flow. Flow rate goes from 0 to the tiniest trickle. The cylinder and applied load slowly creep forward. This being said, the movement of the cylinder and applied load steadily increase as applied voltage is steadily ramped up to positive 10 volts and the proportional valve is progressively opened more and more. Let's say halfway through the ongoing ramp-up event, the cylinder extends far enough to hit LS2, 2 inches into the 8-inch stroke. No change in state is observed since normally open contact CR2A is still in the deactivated open state. Leaving the reset region of LS2, LS2 recloses. Another couple seconds later, the ramping event finally reaches full positive 10 volts and the proportional valve fully opens. Flow rate reaches a maximum and the cylinder obtains maximum speed. However, let's say it only stays at maximum speed for the briefest of moments. And 6 inches into the extension stroke, the applied load strikes LS1. LS1 opens and the coil of control relay CR1 is de-energized. The contacts associated with control relay CR1 immediately return to their deactivated states. Contact CR1A opens and removes the holding circuit. Simultaneously, contact CR1B opens and signals the positive ramp generator to execute the slow 10-second ramp down. Applied voltage to the linear force motor slowly drops from positive 10 volts to 0 volts, and the spool is slowly shifted to the closed center position. Flow progressively decreases. However, the cylinder is still moving in a forward direction. Leaving the reset region of LS1, LS1 recloses, but no change in state is observed since contact CR1A is still in its deactivated open state. Although still moving forward, flow progressively decreases as the proportional valve is slowly moved to the closed center position. However, the decrease in flow rate is not fast enough since the cylinder is still moving at a pretty high rate of speed.